Slater Condon rules. They're all about that we have two determinants, and let's call them, in the general case, K and L. And we're interested in matrix elements, integrals of these determinants, either just the overlap or with some kind of a Hamiltonian, some kind of an operator. And the first, of course, is then the overlap between two, which means this integral, these are Slater determinants, and they are made from the same set of molecular orbitals, of course. It's a much more complicated story if they are different orbital sets, but it's the same set of orbitals, same set of orthogonal, orthonormal orbitals. So the overlap is very, very simple. It is equal to 1 if it's the same determinants, and it's equal to 0 if it's two different determinants. Which means if there's only difference in one orbital, so one was hard to fuck, the other one is single excited, that's it, that's 0. Then we have a matrix element. What these, I mean, they are very often called matrix elements because if you have several determinants, you collect them sort of in a matrix, which is the matrix of all the integrals over the operator in this basis. First matrix element of a one electron operator. And with one electron operator, I do not mean that I just have an operator which depends on one electron, electron 2 or electron 1, but I mean that it's of course a sum over all electrons, but each term in that sum only depends on the coordinates or the spin of one electron at a time. So there's no term which depends on two electrons. So that's a one electron operator, and let's call that O1. Now I have to look at two kinds of matrix elements. Either I have the same determinant on both sides, let's call it K here, it's the same. Then you can calculate, or you can use the Slater-Condon rules. This becomes a sum over all the orbitals which are occupied here, all the orbitals which I have in this determinant. Obviously you can't get sort of a contribution from orbitals which are not there. So it's all the ones which you have here, which is so called the occupied orbitals. And then you actually get an integral over spin orbitals, here that's the spin orbitals, over one of those operators. So to make it quite clear, let's say I write it up, this is just an orbital, so it's a one electron function, so it depends on the coordinates of one electron. And whether I call this electron 1, 2, 3 or 15 or whatever, could call it prion if I would like to, doesn't make a difference. They're all the same, but I have to put something, and there's always an electron 1. You start normally counting with 1, so therefore typically people write it electron 1, but it's the same if you would write 2, if there would be 2. So this would be then 1 here, psi I 1, or you could write it much shorter as the sum over all I orbitals, and then you could write it I, H, I, like this. These are spin orbitals, in case you wonder why there is no factor 2. So you sum over all the orbitals which you have in here, and the corresponding integral over orbitals. This is a one electron integral. This is an integral over 4 coordinates, 3 space coordinates of that electron plus the spin coordinate, whereas this is an integral over number of electrons times 4 coordinates. The 3 spatial coordinates of all the electrons plus the spin coordinates of all the electrons. So this is an extreme reduction in complexity going from this many electron matrix element to a sum over 1 electron integrals. Now if the two differ by 1, how did I write that up? Okay. I think that's the reason why I didn't have the K. If they differ by 1, which means here I have replaced an orbital I by an orbital A in the right hand, then it gets even easier, because then I just get this single integral, which has the two orbitals which are different. I mean, this means in this determinant I have an orbital I, whereas in this determinant I have an orbital A instead of. And it's precisely this one which comes out here. All the other contributions disappear, so it's only one. And if they differ by more than one orbital, it's 0. Then the matrix elements of a two electron operator. Now what is a 2 electron operator? Well, that's an operator where each contribution we have to sum over all pairs of electrons, because the operator, how do you want to write it, each term depends on 2 electrons. And the example we all know is, of course, this operator, the Coulomb potential operator, which depends on the distance between 2 electrons. So you have 2 coordinates in there, I and j. And let's call that O2, the 2 electron. Then I can have again the case like up there, that the 2 determinants actually are the same. And now again I get a sum over all occupied orbitals, all the ones which are included in here. I actually get it twice, well, divided by 2. And then I get a pair of integrals. I get now integrals over these operators. And if we use the notation for the integrals over this operator, which sort of, if I have a spin orbital I, J, 1 over R1, 2, or 1 over R1 minus R2, psi whatever, K, psi L. This we normally write just as I, J, K, L, because we're too lazy to write this. So this single bar in the middle indicates that one. You might have seen a notation, this is sort of my mathematics box. You might have seen something like this with a double bar. This is just a shorthand notation for this, where I have also the exchanged version in it. So the first bar is that one, the second bar is the minus sign plus the permuted one, where you permute the one for the 2 electron, for the electron 2. So using this notation, because the G I think of is this one actually, I get IJ minus IJ JI. One of these double bars, the IJ with the double bar. But I get a sum over all i's and j's divided by 2. Now if they are different again in 1, and you would still get the same. I mean, if there's another 2-electron operator, and there are other 2 electrons, as soon as you allow for spin-orbit coupling, you get other 2-electron operators where you have sort of, it's another property of the 2 electrons, the spin of electron 1, or the angular momentum of electron 1, and the angular momentum of electron 2. You get the same combination here, then just you have a different operator sitting in both integrals. Now if I have this one where they differ by 2, this double sum now collapses again, like here the single collapses to 1, here now it's one of them which disappears. So now we have just a sum over all j occupied, and then it's ij, aj minus ij, ja. Because what used to be I on the left-hand side is still I on the left-hand side, but what was I on the right-hand side is now A. And there's only one of them. And then finally, it's a 2-electron operator, so I can have a difference in 2. I, J, A, and B. And then the only thing I get out is IJAB minus IJBA. And if there would be 3, then the result would be 0. So that's where, because here you have a double sum, single sum, and single term, nothing. This is sort of the Slater-Condon rules. And that's the reason why we say if I have a Hartree-Fock and a triple excited, and we just have our normal Hamiltonian, I don't need to look at that because that's 0.